Okay, so in the last lecture we've been still working on our own implementation of an IPC mechanism for Windows using ALPC ports, which are a Windows proprietary mechanism, mostly undocumented, but luckily there is enough reverse engineering information available, so we could create here this definitions files with the required function prototypes. All those functions live in the NTDLL, which is a core part of the Windows operating system, and we implemented a large portion of the server and most of the client during the last session. So now we will continue implementing this so that at some point it will be fully functional. The mechanism currently is such that we have a server object. So similarly to the QLocal server that is known from the standard mechanics, but it's just made to look like it. It uses own sockets. So we have here our Qt port socket instead of QLocal socket, and this thing is derived from a I/O device, so that we can read and write to it like to a file or any other I/O device derived class. So like sockets and other mechanisms like this. And during the last lecture we've been working on the part which accepts connections. So we go back again to our server, and we have here some place, where is it here, the get next connection mechanism, which gives us the ability, this we don't need, I think, so we can clean up the code a bit. The pending connections are saved on our server object here on the Qt port server private, so don't need that function. The rest of the mechanism already works well, so we can run it and see this part in action. What is still a major work in progress is the sending and receiving of data. We have a what did we broke the last time? Some perfect. We are missing some. Create, and we add create to the. So helper create seems to be. That should work. Helper. This is. That should be defined as protected. Otherwise, it will be treated as a private. That's doesn't like it. Let's just make it public for now. Although maybe we should fix this correctly. So the problem will be that the constructor is something that is only available to the friend objects that we have here, but at the same time, when we use this, where was it here? This create function on the smart pointer, it is called from a different location. So what we need to do is use our smart pointer, and then we will use the normal call to new. This way it is called from a location where it is allowed to be called from, and voila. Okay, so let's start the server, let's start the client, and we see here already the communication is starting. We have received a connection request and then we trigger our own connection. Then we get another request here, which will be for a data package, so that some data are incoming, and here the port request part is not yet implemented, so we have the message that we have sent, but what we are missing is now a mechanism to pipe this message to the rest of our infrastructure. So first things first, we need to get from the message the actual data part. So when we go back to where this is called, the message object here is of type pod message, which is basically a header and then followed by the actual data. And we have been sending here, of course, a standard hello string. So we more or less know what we expect to see, and so it will be easy to see whether we are doing everything correct. The function here receives also a pointer to a client structure, which is this one, and the client structure then has here this helper object, which is referred as a held as a weak pointer, which points to our port socket, and through this and contains the relevant buffers. So the idea is that the client structure inside the server and the socket, wherever it might be held, are referring to the same helper object, and then they can exchange data through it. And the way this is implemented with the strong and weak pointers is that the helper object, being referred here by a smart pointer, will live as long as the socket is in existence. When the socket goes away, the object will also be deleted, and in a thread safe way, the weak pointer here will be invalidated, so that if we try to do something with it, we will properly get a null object instead of getting into a undefined state. So I think this we will not need, since we have defined the buffer somewhere else already. So let's clean this up. Hport we still need. Sequence we might need depending on other things. The in-use flag we will think about later. So I added here a few things which looked useful at the moment, but maybe we will move some more things into this helper which we have introduced during the last lecture. So let's go here. So we are getting our message. So first thing we might want to do is to get from the message the actual data. So let's see, port message. I'll open this on the side so that we know what we are doing and what to expect. So we will probably want to add some additional information to the object when sending data. So let's strip this off first. So stern msg data long asterisk so we are casting the object from this type just to char, and then we are adding to it the size of this thing. So we get the data, so we get a pointer which points directly after this header, which is part of the standard communication that is required and defined by how Windows operates. And from here, now we have defined this as ulong, so that we can add 32-bit integers from it easily. But in principle, we could also format the message any other way we want. Let's use lowercase data here. Using such a ulong is just simply in this case a bit convenient. So we would define that the first character, sorry, not first character, first ulong which we are sending will contain the length of the entire package. So total size 0. Then, as you remember, we had the sequence number which we'll be using now. So sequence is equals, that will need to be filled in on the client side. This part is not yet completed. Let's say that the sequence number will be the third ulong. Or let's change a different distance. We here only have a uchar for the sequence number. Let's say it will be let's make this a little bit more elegant. Uchar msg row, so that we can refer to those things in with different granularity. MSG structure. That's good enough. Yeah, message and message data. We will only use the third character. So we will take a part of the length field and mask it off, so that we can use it for a sequence number. This will limit the maximal communication length to about 24 megabytes per datagram, but for our use case this should be good enough, and if we want we can later change this to be a different size. Or maybe let's change it slightly. Let's leave it. For now we leave it as is, and if we want to change something later we can always modify it. So we get our sequence number, which is quite useful to ensure that if there is some hiccup with the communication, we receive the same package, that we can then dispose of it, or if we receive something out of order, that we can also detect this and then handle appropriately. Since this mechanism is not documented, even if we, for example, observe that it always appears to deliver messages in sequence, and even if this is true for a given version of Windows, there are no guarantees that this will not change in another one. So always when using undocumented features, it's very recommended to try to design a fail-safe implementation around it, so that if something starts behaving differently than it was observed before, that it does not end up breaking the mechanism, or worst case breaking it in a way that so breaking in a defined way that triggers a clear error is fine. Breaking it in a way that we will start receiving garbage data and not even notice that, this is not fine. So such safeguards like maintaining sequence numbers, checking lengths, etc., is quite useful here. Okay, so we have our length. Later on we will write down a package format for our own data that will also be quite useful. Right, so let's check. So if we have gotten some data, so with total size, and let's make a safeguard. Total size must be larger than well, here we have a ulong. For now we only use one ulong, so it must be at least 4 in size. In principle, of course, this test making it first kind of doesn't work, but what we work here on the assumption that we always allocate a slightly bigger amount of memory, so we can at least try to read the size and then see if the things are consistent. If they are not, then well, if they are not, then they are not. And then what we also know is that we have a length field inside the original port message, so we can check this as well. And total size is greater or equals msg union1 struct1 data length. Right, and if this is all true, then we can just add the data to the buffer. So we need to grab our client, client helper.log. The log on a weak pointer generates in a thread safe manner a strong pointer, and the way it works is it will either success and generate a strong pointer which is not null, in which case the reference on the object have been increased, and even if now the other object goes away, the with the other object that holds the strong pointer goes away. Here we are now holding a log, so now the client helper will remain valid. So if the other socket would be just deleted while we are executing this function, the result will be the helper will stick around, and only once we are done with using it and remove our own reference, then it will be deleted, which means we are doing some work for the garbage bin, but that is better than risking some undefined behavior or crashing the application. And the log returns us, so the way this works is the log returns us a strong pointer. So we just instead of typing the whole name, this helper, and now we can use our helper safely. The helper has let's see, so here is our structure. Let's quickly go to the helper again. yeah, since this is protected, we also need to define access. Was this a struct or a, it was a struct. So struct. Since we want to be access to those, since we want to be able to access those three variables here, we need to define our thing here as a friend as well. And now we can buffer mutex q. Let's see what to do. We define just a mutex, so q mutex okay. Q mutex lock reference. So the object, the mutex lock, is a helper, as I showed it already in the last lecture, which just acquires a mutex, and when the object gets destroyed, then it releases the mutex. So using it ensures that we don't forget to release it, which would end up in a total deadlock of the system. Okay, and now what we can do is we can add the data to our actual buffer. Receive buffer punct. Let's see. Yeah, append. And there's one thing we should also keep in mind. That is, if we are sending, which part of the datagram we are sending. So we will need a helper variable here. We need a helper variable. So if we need to differentiate between the case where we are receiving the first package of a message or a subsequent package, and for this we'll use a helper variable, which will simply be false by default and set to true once we have received an initial message. Okay, so we do this, then we have the buffer, so we need to, the buffer may already contain other messages, so we need to first we can reserve the size that we want. That will be the total size. Okay. Good. Then we also need to handle the case if this was wrong, so something was malformatted. So here we will just switch. We'll set the sequence to 0. And we'll break the whole thing. Return. And since we are supposed to send at least some sort of reply, we will see, maybe we will, maybe not. For now, this is it. So if there was an error, we bug out. We put the breakpoint here so that we can notice this case. And then we can actually append the data to our buffer. The one thing we need to keep in mind, the log here. Let's move all of this here so that we can, so that we maintain the log all the time and that we have our help available all the time to make it more convenient. Punct append. Right. So we just append here our UChar message. Plus and the current length, data length, which we got here. I think this one's just char, not UChar. No, append. Oops. Doesn't this work? There should be an append that takes yeah, const char. Just not uchar. Just cast this to char, then it should be happy. And this thing, this was defined here, so this we will need to define outside. Yeah. Okay, so this will add this. We should keep our header, which for now is just one u long long. So let's make this +4 and here -4. But this is something we'll need to later revisit to ensure that we don't have any mistakes in this part. So we have our client, we had the data. And since we don't really care for rebuilding entire packages, since we want this to emulate a streaming mechanism, what we could have is here some code that actually checks whether the thing is complete. But since we kind of don't know how much to send, we will need another helper variable. Actually, we can change this one into a long receiving size. So we'll just write down the size we are receiving right now, and this will then be, so if receiving is 0, then we will set receiving here, if this is the first package, to be the total size, since we on from the client. And then we know what we'll also need is something to count how much is missing. So what we'll do is receiving size here minus equals let's make here another helper ucha message data will be just this thingy here. Keep the conversion here, we prefer ucha long ulong msql msql is data length -4, so that we have the indexes in one place. We can later introduce a structure to define our header. And then now when we operate with those variables, we are on a safe side. And of course we should always check if length is greater than this thing, then something is wrong. It should never be greater, it should be at most equals. But in this case we just set this to 0, put a breakpoint here, and else we subtract it. So our receive size will shrink as the subsequent packages of one larger message are arriving. As you might remember from the last lecture, our message length is quite small if we want to be compatible with very old Windows. Newer Windows versions can go up to 64K, which is big, but still not as big as our current 24 megabyte limit. And if we would move the sequence, well, actually we could do it right now. Let's increase this. Let's make it bigger. Let's use 2 longs for that. So now we increase actually our limit to a gigabyte, which sorry, to 4 gigabyte, which is more than enough. And our sequence number will be just the next entry in the row, and we can then define. We have still three more spare bytes what we can use for something else. So yeah. So in any case, we will need to usually reassemble multiple messages before everything has arrived. Good. So we have this help buffer, and once this reaches actually null. So in principle, we could of course each time we receive something trigger an event notifying whatever is listening that they could already read data. But since here we want to, even though we are using a stream protocol, we want to at least make it a bit more convenient. So we will just delay the notification. We just keep the data here in a buffer cached, and only if this is null, then we will issue a notification to our socket. And we can do it by emitting this ready read signal on our helper. So emit helper oops, didn't take helper, copy, read. Okay, and as soon as we do this, so let's put a breakpoint here. Then we'll see what else is happening. So this should trigger then the client side to actually read everything, and not the client side. We are sending from the client. It will trigger the socket on the server side first to emit a reply. So we create the server, we create the client. Let's close. This we don't need. So we establish the connection. We have here on connection event. Then we have already a request, and it didn't work. So something is wrong. Probably our sending of data. We have some. Yeah, we changed here the length and stuff by 1. This of course we already had some sender code in the socket, so now of course this will not be consistent. So let's maybe be here a little bit more proper and define our header structure. S port header long total size char sequence, and then we will keep so this, if we hover over the thingy, it will tell us that this is not quite right. It should tell us that this thing is 8 bytes. As you see here, it is 8 bytes in size. The reason is the alignment. So it also told us which alignment is used. By default, it's using the 4 bytes here, and this means that even though here we only use 1 byte, it will allocate 3 more, so that we have a multiple of 4. This is how the padding works. So we can create here a reserved array of 3 bytes that will not increase the size, since those were already reserved either way. And it is more illustrative, so that we see where we could put some more data if we decide that we need that. Okay, so we have our pod structure. We go back to our server. We have here our data. So this is the raw thing as we receive it. Then we will have our header, msg hdr header. Just cast this to, and then we want our data, our actual data, so that 2 goes away. Oops, one's too much. And length. So oops. So message data is then of course this thing plus size of this, and the length is basically what we have read from the data length minus what we, so data length is the message of the size of this one datagram. If we had multiple broken up, this will not be reflected by data length. It will be in our own header. And from this, of course, here we need to subtract the size of this data. Right, the rest remains unchanged, and now we need to just cleanly implement the same thing here in our client. So we have some data that we want to send. Let's see, we have a request buffer, response buffer. So request buffer is what we are sending. We have here our header. So the header is again the port header, this port message thingy. Then our own subheader, so to say, will be placed. So we have here our request data, which is just the buffer plus this size of port message, which is the size of this, well, port message. As you might remember from the last lecture, if we would be mixing 32 and 64-bit processes communicating with each other, this message size will be different. So we need to dynamically determine it, which we are doing somewhere at the beginning here. And then once we have done this, we can use this value. Although this determination is only needed for 32-bit processes, it's here we have 64-bit. We just assign the known size, and this is fine. Right, so we have this, we have this, so we have our send len. This is how much data we actually want to send. The data max is again a helper variable where we define the maximum size that we can communicate. So this value will be provided here by the NT connect port function, and from it we need to subtract this header size, which we always have to put there for what the protocol is concerned. So this send length, yeah, and the idea of this send length is that it is the size of one packet. So we will be basically just slicing the data down into packages of this size, and then pushing them through the pipe. Right. So we zero everything. We set our send length here. Then there is a total length parameter, but the total length parameter in this case contains just also the port message header, not only the data which we are passing to the whole thing. So it's not the same total size as what we will be writing further down into the whole mechanism. Right, so we have our send data. So now we will need to create our own package header. So as we see here, this package header we will be processing. Alright, we wanted to use that. So sequence can be this, and long will be total size. One thing to consider is whether I want to send this header in every single package, or if we want to send it in the first package and then just send subsequent packages without the header. Here, since I think the most elegant approach will be to attach this header every time, and then in principle we could also validate whether the data are still consistent, but this is something we can do later. So when we go to our socket, right, we will need to also define the header, so we can copy some things from here. Socket, yeah. So we have here our primary header, then we have our subheader, that will be the uchar we have, header port, yeah. This goes away. Request data is the thing this thing points to, and message length, of course we know this is what we have computed here. So data, message data. We should work then on the consistency of our naming scheme. Right, so we get this, we get this. Then we can this will need to be refilled. This will be refilled each time this in a loop. This is fine. So here we had our sequence number is equals. For now, let's use a random value. We will later fix that. And also the sequence number, it is just a character, so it will run up to 255, and then it will wrap back to 0, which will be considered valid. So it's just to see if there are some issues on a smaller scale. Total size, of course, need as well. Total size is len, so that we know how long the whole communication will be. Right. This and then we are here data data, but data we want to copy on message data. Oops, with the send length which is just for the current iteration. Then here we can increment data and length by this amount, since increment the data and decrement the length, and we will just loop here until the whole thing reaches emptiness. And then here we have the reading part, which we might still work on a bit later. Let's run it. Okay, what's wrong? It doesn't like ulong because this is defined on the Windows header. So let's define unsigned int. Let's just define those things explicitly. Then it will be compatible with everything. Okay, so again, server client. So we are here in our connection establishment. We should put a breakpoint in port server here so that we can step through the request. We could remove the other breakpoints, but that we will do later. So we here have a request incoming. So we get our header. You can see what it contains. Okay, so it says total size is 6, which probably is correct. This is basically 1, 2, 3 in hex notation, so this is fine, and reserved is just some random text because it wasn't initialized. So we have here, this didn't work out quite well. Data length, we have set the wrong data length. We forgot our header, so we need to fix that. Here somewhere. Right here. So we have here our send length. So we will need to add to this this size special length plus size of port header. And since we have defined this here and we don't want to complicate things, let's just go like this, and here let's change the order just for just of send. Then it also means we need to adjust our max data len by removing the own header size. So we reach it here, we subtract this, and here we will subtract this as well, because we need to take account for both headers, the Windows header and our own header. Okay, that already might have fixed all the issues. Let's see. So server connect. We send a request. This we are not interested in. This we are. Okay, here we step. So we have again our header. This should be unchanged. Which is then we have our data, which is hello \n. So 6 characters, that looks fine, and message length of 6 is also correct. So we have here our receiving size. We see that this is 0, so we get our length, we get our sequence number, then we check if everything is correct, and it is not, because y6 total size, yeah, because we here forgot about the header, so here we should check, we should improve the text. So first of all, there must be a total size. Total size already includes header. We want this to include the header. We don't want this to include the header. So let's just do it like this. We only check if there is anything to be transmitted, and else we just put a to do here, to do for later as for error handling. We only check whether total size is valid, and we says yeah, that should be now fine. Let's run it again. So run server, run client, we send some data, we process the data, zack. Total size is not null, it's 6, so we resize the buffer, we set what we expect to receive, then we perform the receiving from the first package, then we subtract this brings us back to 0, so this is correct, and we will trigger the ready read. So let's see here, port client, port server, connected this with this, so let's put a breakpoint here. So this is now ready to emit the signal. Here we are, this is fine, and then we run. So the other one, it's always things happening in two threads, so sometimes the thing jumps around. And the thing we saw before was from this client side. Here we are still on the server side. We have now some data to receive, but our read all will fail since we have not implemented it yet. So our buffer here is still empty. So we will need to work now on this part. So we go to our port socket, and we want read data. Actually, we didn't trigger. That is not great. That should be triggered. Let's quickly step through it. We probably need to update. We will need to update a variable somewhere which will tell us how many data can be read. This is triggered, and we are done with the sending. And here we are trying to receive something. Let's see. Source qt base. Okay, so here we are inside the read function. Creates an array, and it bugs out. We need size needs to give us something back. Let's rerun this. Server. Oops, that wasn't correct. I pressed this once too much. Let's try it again. Server start. Okay, let's put the breakpoint here where we want it anyways. Okay, we go in. This bugs out. Check readable. This thing already bugs out. Didn't we open it correctly? Apparently we did not open this correctly. Oh, we didn't open it at all. That might also be. Let's review our connection establishment. Port socket. Port server. So we have here new message, new client. From clients we take one. Client is here, then nope, where was it? It was somewhere pending connection, expanding connection. So we take this, we set this, and we forgot to open it, so we need to not the client, the socket. We could of course put the opening function into this. Let's do this. Open for read and for write. Yeah. Server client. Okay, now we try reading. Let's see if this will work out. Yeah. So here now we enter our read function, which in this case returns an error, but the next step will be to make it return the data which we want to read. So since this function here might be called from multiple places, we will on our helper need to log the mutex. But one thing first, we need to check whether we actually have a we need to check that. Actually we should always have a helper unless we have not initialized it. No, we always have a helper. Okay, so the helper always exists, so we don't need to check for its presence. So really we can just start reading from a helper. So we start with qmutex log. Was it just log? Qmutex log. Okay, yeah. Log, that doesn't matter here. Reference helper underscore buffer mutex. So now we can safely access our buffers, and from here we are reading, so we are going from the receive buffer. So now we need to determine how much we want to read. We can reuse this variable. So if max len is less than buffer size, then max len is just equals buffer size, and we do not expect here any other issues. So we will, if this is empty, we'll just return null. Otherwise, well, not. Okay, so if this is not null, so that the function, the way it works is it returns 0 if nothing was read, the amount of bytes that were read if something was read, or -1 on an error. We don't expect here any errors, since the helper object never goes away. We could of course later set a flag when a disconnect happens, such that if you then try to read it and then you see the flag on the helper, then here you would bug out. But for now we want to keep this simple, so we don't do that. And so we only need to copy into data from helper source punkt const data, comma max len. And this is now a part that will be a bit inefficient. We need to remove from 0 to max len, which triggers internally a mem copy. Older versions of Qt had a not publicly exposed, but as a part of the private headers available ring buffer. Once here everything works fine and we have still some spare time, we can look if we can access it and use it. A ring buffer has the advantage that the starting point is basically dynamically being reassigned as you are reading from the thing. The downside is that the ring buffer has a maximal limited size, so growing a ring buffer is kind of not something that one would do, in contrast to our approach here. Our internal buffer that we're using here, we can grow it as much as we like until we run out of memory, which, well, one can do, but of course one would usually try to avoid it. And the only downside is that whenever we read something, we need to copy all the data. So if there's a lot of data inside the buffer, the copying operations will waste some CPU cycles, but it's, I think, a worth trade-off for the gained flexibility. Okay, so let's run it again. Server, client, continue. So here we are trying to read something. This is okay. Max len is not okay. It was a mistake. It should be if it's greater. Then we assign it. Zack, again, zack. Okay. Zack. Okay, now it's correct. Let's jump out. Okay, and then we have in our buffer local sp data value. In our buffer we have now the hello text, and as you know, this will then trigger in our what was it, port Qt port server motivated to reply. So we want to write something, basically the what, which is an unpolite reply to a hello. And this will again now bring us to our psocket, but this time to the write data here. And we have two implementations, write data client and write data server. So depending on where we are, it is a different thing that happens. In case of write data on the server side, we just put this thing here into our send buffer, and that's it. While in the case if we would be on the client side, we would try to send it directly without any buffering. So we put a breakpoint here to see that we arrive. with the right content. And this brings us to the first complication, being that the way this worked, the server part here already processed this request, and it did not schedule any response to be sent back basically to the client. So the server is at this point not aware that it should send something. So let's see how we proceed with this. So um, we could in principle what we will want to do is we will want to set this replying flag, and then if another communication comes in from the client, we will then be able to send the data back that were sent in this reply. This is of course not quite ideal, because the way it works is that the client would need to somehow pull permanently whether there are data available um, for communication or not. So we will need to solve this later on, but for now let's first work on this reply part of the mechanism. So let's put here and here a breakpoint. Actually, we can just keep the breakpoints inside those functions. Doesn't matter. Better too many than too few. Yeah. So we go back to our socket, and here, right. So what we probably should change is that instead of using a replying flag, we could acquire a log to our to our helper, and then check whether there is something in its buffer, because otherwise we would somehow need to synchronize those two objects. So we can write things to helper, but we cannot write things to this as client, and vice versa. So we'll just remove this replying here for now. Sequence will leave, that is fine. So let's go, we could make a function which, let's keep this, and let's make another change while we are on our way here. We will often need to refer to this helper, so it will be more convenient to just pass the helper here directly. I'm not even sure whether we will be interested in the client that much. We could move probably everything that is on the client into the helper. For now, since we're not sure what we will do, we'll just keep it flexible, but I think we will, in the next iteration of this implementation, just clean this up in the suggested way. So here we are finding a client, then we are getting our helper, and then we can, first of all, the whole thing is locked, so we can safely operate with our helper. And then here, the helper, let's just define a function. I mean, it could be also a variable. We can also directly just access m. Can't we? We cannot, because this is a global function. So let's really go with this replying function. This will be a more elegant approach, because this function, since it's read only, it's quite safe to just define it publicly. Oops. For is replying const return send buffer punkt use m, and it should have a size is greater 0, or is that not equal 0? It's the same more or less. Okay, so if this is the case, then the replying will be set to true, because we have something to send back. The mechanism here is made such it will just answer with an empty reply if there is nothing sent. And before we work with fixing the other mechanisms, I'm thinking that we could try to make this work without additional synchronization by just ensuring that if we emit from here this ready read, that this thing will end up triggering the send of the reply before this here resumes. So we can try if we can make this work. Okay, so let's see. Server. So we have here ready read. We connect this thing, and here we will want this as a blocking connection. So Qt queued blocking queued connection. Okay, so if ready read is triggered, then on data, but there is one more caveat. The sockets somewhere here we are like kind of proxying this request, so we are connecting the ready read of our helper object, which is just our own. We could give it any name with the actual ready read of our socket object. So with this one, and as a blocking connection, this should actually work. Let's go here. Let's put another breakpoint there, and let's see if this works as expected. So server client. So we are sending a message out. We entering our function. We are now triggering the ready read, and it's screwed up because we need to unlock this thing. If we don't unlock it, then the other thing will be blocked. Unlock, but this might still not be enough. Let's see. Zack, zack. Nope, it's still blocked. This is the server side, so it's blocking on the server side. We can investigate the threads. We have a bit many threads. Most of them are just automatically created. So the main thread is blocking in. That is nowhere. This is fine. This is fine. This is fine. This is fine. It might be also that it just didn't like our. Interesting. It doesn't seems blocked, so it looks more like it just did not. Yeah, here, Qt deadlock detected. Just did not execute the event. Okay, so this workaround might not be that easy. It doesn't. So basically, what it does in such a case, it does not execute this event, and then nothing happens. So it says it would be a deadlock, but it ends up not doing anything. But this thing is called from an own thread, so this should be safe. Then it triggers an event in the. It's supposed to trigger an event in the main thread. And we can check how this behaves if we remove this redirection. But I think then it just will desynchronize everything, so it might not. Now we of course have a read error because this tool here is blocking access to a file. But it releases the file after a short time, so we just rebuild a few times. Okay, so try again. Oops. No, but now we just emitted it instantly. It still didn't like this. Okay, wait, so let's try a different thing. Let's here make this non-blocking, the other one. That might be the problem. Because those two are kind of living in the same thread, so that might have not been correct to do that. Okay, zack, zack, emit. Haha, now it works. So we are call stack here, read all here in this thing. Then we will make this read data, max again, write reply, which adds something to the buffer, and then only it gets unlocked. So this was a bit hacky, but should be quite good. So we continue. Now we should be seeing that there is something to be replied. Then we enter our port replay function, which again does not do anything. So this now we need to implement this function. And before we do this, we then take a look what we have implemented here. I think the simplest approach will be when we just duplicate the sender side, kind of, on the other end. So we have our, but just it will be then the response, not the request buffer, and so on. But before we do that, any questions so far?
No, not yet.
Okay, so let's now continue with this part of the whole thing. Right, so we need a buffer. Let's just response, copy this in here. We don't have message size, so here we are on the server side. So here we will go with just using the known values. Yeah. So the idea is here a bit simpler. So on the server side, we will just assume that we are always the native platform bitness. So we don't assume a 32-bit server on a 64-bit process. This would also not be necessarily a supported scenario given how the whole communication is designed on the Windows side. Right, so we have this thingy, then we need to set one header, set the comment, set port header, set you either call it message header or custom header. Now we call this a port header. Then let's set set message header, set custom header, so that these things are reasonably clear. We don't need a second loop. We only need this part and everything. Right, and we also need the two variables like data and length. So let's grab them quickly. Okay, so we have we don't have a lock, so we need to make one. This can stay as is. This unlock is required, so we take this. Helper m underscore now this one times is the send buffer punct const data helper send buffer size. And here what we will basically do is just send everything that we have. We will not be making any additional breaking apart of things. So once we are done with the whole thing, at the end we can just clear the buffer. Send buffer clear. Okay, right, so we have our data, we have now, of course, everything that has to is a request becomes a response, so that response data, right, and of course then we need to send them out. function for that. Let me quickly look it up. Message, this goes to client, send the buffer. For server target. Out message. Nope. One moment, please. So this port send we want to trigger from this. We got our data from receive, and then should be a reply. We have a reply message. We might need to write into this reply message. Yeah, this should be reasonable, but we can only do one iteration, so this gets complicated a bit. Right, so the message we have here is our entire reply message. So this thing will be then sent during. So we need to ensure that we only write one set of data into this message, and then during the next iteration of the loop, it will be sent by this thing. So this we need to change because we cannot. Basically, what we want is to write into this thing here directly, and we can only write one iteration. And then we need to wait for the next empty message to send the next iteration, and so on and so on. So we should actually then, so this stays, this will not be, this will be again a remove 0,len. And we just should cleanly re-implement the thing here. Right, so we have our message space, this will be here. Response buffer was defined as a image, right? So this we will need to cast to a then. Although in principle we could just also go with this just +1, but this is not elegant, so it's and the compiler will optimize this away anyways, so that it does it the most effective. So here we have our response data, the loop goes away. Right, so max data len, that is port message length. Let's define this here. Const is equals port message length minus this and minus this. Okay. This is our max data length. So the compiler will basically evaluate into one single number and then just insert the number wherever appropriate. So it will not waste resources. Right, and here's the same thing. Alright, so we can actually just use send length, and we don't need this since we're not going a second iteration. Alright, so we have our send length. We prepared the header. We memset everything so that everything is null. We set length here again. Port message size. This is let's quickly investigate one thing. Nope. Socket here. Okay. This should be fine. Okay. Header data. Reply data. Okay, then it should be fine. And the whole thing will, once this here reaches 0, becomes empty basically, then it will automatically clear the replying flag, since this is contingent on the amount of data contained in the buffer. We don't need to release the lock or anything, since it will be released anyways automatically and we are not calling anything else. And then what we will hope is that once it works, we will here end up then in this second loop here and receive data. So what we then necessarily need to test once this very basic mechanism works is that this putting together of multiple packages, that this part of the mechanism also is working correctly. Okay, so let's run. That might not necessarily work quite right. This thing does its thing. This thing does its thing here. Then we emit. Yeah, this is fine. Write data. Then we arrive at this breakpoint. Then we exit this. Then we go to our reply. Then we create the reply so we can watch the memory as it's being written. Zack. So some things changed. The what is now part of the buffer. And then we go up. And here. Wait, we should not end up in yeah, and we end up in replying. This is correct. So then we repeat that. And something didn't work out. Let's try it again. Okay. Let's fix it later. Let's first see why this doesn't work. So we start. We get here a process port message. Then we do this thing. Then we send the data. We should remove some of the breakpoints. Then we are here in this next step. Okay. Then we end up again in our send buffer. Why did we end up in send buffer? Because this thing runs asynchronously because there are multiple threads processing it. End up in replying. Okay, so for now let's go with removing most of the breakpoints, because this just complicates things. We can just uncheck them so that they are not lost on us. This one we want to keep. And which one we want to keep as well. So this one and this one, and maybe we add the breakpoint here. Or actually we could just put it here and then we can just step from there. Server, client. Okay, so we have probably somewhere a bug with the memory access, because apparently that is happening. local. Oh, this is null. This is null. It's not good. Something caused our client to go away, and then this thingy becomes null. So first of all, we need to check whether this thing is null, and then we need to know why it would disconnect. Although we are not sending a disconnect message anywhere, so let's go to our socket, pod socket, and put a breakpoint into the and put the breakpoint here. So server, client, I think. It is not working quite as it should. Let's see why. So let's activate this breakpoint. Pod, connect. Maybe we actually have now something open that stack open. Nope, all the networks are closed. But it worked already before that. We reached here to read the data and so on. So something else is now not working. Let's see what we could do. First, let's check first, let's just start and observe the handles that the thing has. So server and client. Server has handles here, my pod, and the client. It claims it has a connected. It claims it has a connection. So something is really strange. Not having breakpoints speeds things up. So let's just give it a bit more time to do something. So we will need to debug. Let's start with this part of the code, the connection, and then we'll start this debug the sending, whether it broken something. What we also could do is to just change the name of the pod, but I don't think this would make a difference. So this part seems correct. It just says connected, and we get a success. And then we try to send, and now it worked. No, I didn't. We shall just step through it and see. So once we trigger this, something should happen on the server side. It also works. It is some timing issue apparently, since otherwise this seemed to work. I guess probably it will be something that we will hear bug out in one of those two cases if we don't have the breakpoint. So this will again probably work. We remove this breakpoint. Server run. Yeah, and we bug out here. So the problem, what is happening basically, we get the connection request, and then the other side is instantly sending us a package. But at this point, the server side did not yet process the event, which will, where is it? Pod socket, pod server Qt. Did not process, where is it? On connection. And thus here we have not yet connected everything. And we don't have a pod socket. We don't have yet a client structure. So this wasn't called, and here this wasn't called. And then we don't have this helper, because this helper lives on the actual client. It doesn't live outside. So we need to change the mechanism either by creating the helper ourselves or by creating the whole client, because the way this works now is when this is triggered after some delay, then we create the client and then we attach it. So then we create the socket and then we attach it to the client, which we have. This way is correct. And this means that the whole thing doesn't exist from the get-go. So we could in this next client um, change this a new array from something that holds just client references to hold also already a helper, and then we would just use a function to move the helper um, into the client, into the socket object. I think this will be probably the more elegant solution. Um, Otherwise, that we could also, yeah, that will be definitely a more elegant solution, because we want the creation of our a client here to be on the other part of the implementation, also such that we might later maybe create some derived object and then override this function. So let's add a fix for that problem. Get next client, and now here this is not, it will be a list of std pair of a client reference, and we also need to hold socket helper. Right, so this helper will basically stick around for as long as this thing will stick around, which is okay-ish. Zack. Okay, so here we have here we push back the client. So std make pair client we already have. Pair helper ist gleich we had here somewhere the helper creation code here. Right, so we create the helper, we attach this here. Actually, this thing should be smart enough to so this make pair is a template, and it just automatically can find out what type 1 and type 2s are, so that it can be written more compact. But here in the client we need to set also p helper to helper. Right, okay, so this is here. Then we have here the part where we acquire a log of front. Oh, we have another bug. We forgot to remove front. That is not great. Front.first is log. Get next client needs to return two things. This is not pretty, but it is what it is. Okay, this is only defined here, so it's a bit less terrible. We need this type, and with a client we need that type. So this will be std pair comma. We could define an own type for this, but let's just don't. It's not longer a pay client. It's a pair of pointers, so it's kind of not great to call it like this. And we go with first. We don't care for the second. Here we just may yeah, okay. Punkt first is das Punkt. So we cannot directly assign it, since one is a direct assignment and another one goes through this log semantics. Then we pop it. So pop front will remove the entry from the list. We forgot to do that before, so that would have been a bug, another bug. And then we return this, and then let's see what this thing is doing. So here we just go to auto, next client. Then we create a socket. Client helper is already assigned, so we will make it like this client. In this case we would actually not care for client, we only care for second. we will improve that in a minute. For now, let's just that should be fine. Socket, socket, socket. And here we have our constructor. We copy it. In another one, we'll create a protected constructor. And this get socket helper from server. This will not longer exist. This should need to be a ref. PTR the helper, comma. Okay. So let's quickly implement it. It's pretty much the same thing, just well, almost. Just instead of new, we are taking the thing which we already have been provided. And that's of course not correct. This should not have an asterisk, and we can go with const reference. Although that should not really performance-wise make a meaningful difference. Okay. Socket, and we had our function, and right, we said open also needs to be in this. So this we set. This open will do somewhere else. This goes away. Pipe server socket open. Qt socket. And we said we will improve on this get next client. Basically only care for helper. Cannot can we? Yeah, we can. Okay, it will work. So here we change this, that we only return the pointer to the helper, and we will change from get next client to get next client helper. Okay. So this next client helper PTR per helper. And why this is not okay, so and why this is not something, this gets returned. So what I'm thinking right now is that if the client goes away before we have triggered here the event, we would have kind of skipped him. But we don't really need this functionality anymore. We could really just store only the helpers here without anything. So let's go with that. That simplifies things. It's not super pretty in every way, but it's pretty enough. Here just push back the helper. Yo. Okay. For now it's good enough. Next helper. Get next client helper. And this of course here is not second, but just the thing. Oops. Right, and this of course might be null. So if this is null, then return null as well. So if we didn't get a next helper and p, if we didn't get a next p helper, then we just bug out with null. Okay, yeah, let's try it. We didn't have terminated the previous instance, so we tried to modify it, which sometimes works. Right, and we end here import request, which is correct. Then we have here our try to receive something. And this was 0. So it's behaving, of course, much more consistent now, but we're still not quite happy. So we have here our message, and we did not enter replying, so there is now some other problem. We need to debug. This was set to 0. Our helper should have something in its buffer. Oops. Yeah, receive buffer, that is correct. So we should now trigger this thingy. Which should server Qt trigger the send here, which it did. Okay, breakpoint, and if this was triggered correctly, then in principle we can step out of the whole thing. Okay, that is a bit too much stepping out. Let's just jump to, we'll just F5 it. Now it works. So it seems to be another timing issue. It would not be quite satisfactory though. Server client. And this. Let's put the breakpoint here. This is also a good teachable moment, because you notice that sometimes when stepping through a code, everything seems fine, but when running it, it doesn't, because the timing of the whole thing changes. So let's see. This kind of looks correct-ish. Yeah, and then we have the thing. Then this. Now it worked. Let's remove this breakpoint. Zack, zack. This works, this works. And it didn't progress. Could put a breakpoint here to see. Maybe we are triggering another condition. Server client. That's the first request, and now we get a second request in there, which is correct-ish. Sorry, the first will be connect. The second is the data. Then we run in here, which is correct. Then we are done with this. So let's see where we go from there. And we get empty. So it kind of behaves the way it should, but we have a somewhere a logic mistake in our in the socket. So because the way this thing works is it kind of sends data in and gets a reply instantly back, but the way in our case it happens is that the first reply we get, the instant reply we get, is empty, and then the whole thing does no longer do what we want it to do. So basically we always need to invoke this at least twice, because first time we will, when we invoke this the first time, then we'll end up in server. So this thing will then go past. So basically the threads are waiting in this call, and when the other call happens, this call in one of the threads resumes execution and does something. Then we go through this whole thing here, and at this point there is no reply to be replied, let's say. Then the whole thing again makes kind of a turn. We prepare the reply for the next go through the whole thing, but we never do this next go through the whole thing. So let's see how we improve that. Okay, but given that we always need to call this, we could maybe split this into two loops actually. I'll put this here and this there. Though we might have a reply, we should not do this. We should really make the loop go once more. Always. We could put this into a separate function, then we could just call it a second time after we are done. That would be one option. It would be a reasonable option. Let's do that. Do we need some special access to something? We will later, but we can do that once we are done with everything. We'll need access to helper. We could define this function. We need access to a few things. Okay, so let's create a full function for that. Port socket. Void receive helper. It will get some additional parameters later on, but for now let's just put it here, and then we will see what's missing. This thing, actually it's not really a receive helper, it's a transmission helper. Just call it helper. I'm too lazy to come up with a good name. Rightio, so we need a total send. And we could just call this and then add this to total send, even if it bugs out. For now, let's do that. So here will be send be set to 0. That will be needed. Although we are not using it, so we can just drop it here. Return. We should maybe return an error code or something. So int return -1 and else return 0. Okay, so the whole response stuff can stay here. We want the request header. I think this is the only thing we need to actually pass. Since we don't have port message defined, I will just use a void pointer. It takes everything. And if we know which type it is, it's safe to use. So this goes here. Helper. This goes here. Right, and if this is less than 0, then return and break. So if this is less than 0, then something bad happened, and then we just break from the whole thing. Right, so we are then in the helper. If we receive something, then we grab it. This will need some improvement because it does not follow our new header architecture, so this will have to go. But one important thing, of course, is we need to invoke helper once more to grab the reply once we have the reply. Yeah. Then we put a breakpoint here and let's run. Create server, connect to server. We get a connection message. We get this, we don't care. We get a request. We are here. this thing was 0. It shouldn't break, it should no, it should break is correct, because this breaks out from the top. Then we see that we are done, and then we try again, continue, and this time we end up here in pod request, and then we create the we ended up in replying again. This is not quite what we wanted. We should have first ended up here, and in the second call ended up there, because helper should have contained some data to be sent. What? Value send buffer is null because we cleared it. We might still need a helper variable. Although not really. No, this will be fine. This should be fine because this should have already triggered a reply. We just didn't arrive yet. It will work. So here let's step into this thing. This should give us a 0 operation. So once we are here, total size should be 0. Oh, it's again 6. That's not good. Okay, something is wrong. We need to put some more breakpoints. Or maybe we just debug better with the existing ones. We forgot to clear the header because we broken up before and we didn't clear the header, and then the next request was wrong. The clearing header. Let's think about it. So we create our request. We invoke helper. We end up in this loop. We send a request. We might get something back, but usually we don't. Then we break out of this thing. Then we clear the header, and then we make helper. But if we would end up here and we would receive something, then we would we need to clear the header in either way after the first transmission. So even though we will be kind of re-clearing it more than once, let's put it here. In the subsequent calls, we'll just clear it again and again. It's not perfectly pretty, but it's quick enough. It's a very small thing to be memset, so that should be fine. Okay, let's try again. Zack, zack. Okay, so pod request this we expect. Then we go here. The first run was with nothing, so we clear everything and we break out. Then we, in the meantime, we're working here. Did we not set a second request? Okay, so now we just process the request. We haven't processed it yet. Oh, we did. Wait, let's see it again in slow motion. So zack, zack. We get already the first request. Helper first is nothing, and we are done with this operation. Let's put a breakpoint here. And we come here again, and now our request should be what was it? S1 so U1 S1. Why didn't we reset total length request header? Mem set 0 because we set total length again. Theoretically this is valid because it's kind of an empty thing with no additional data. So if we come here again, we go in, we see that this is null, then we get here total size should be this time, this is not right, this is 6. This total size was also 6 and the length was negative. Yeah, because this was 0. So we need to check whether this is the case and then bug out early. The message header. Okay, before we do this, so in principle we could move this logic here if is not replying. And if this is not null, then we process this, and this should fix that. Try again. Server message. So we send the request, we process the request, then we go into preparing the reply. And it stopped at that. That is also not quite ideal. Let's run it again. So connect. Right, so here, and we should enter this function twice, once from here, which we already did, and right now it once from here. So this thing sends the request. Here we prepare the reply. The thing will be now pending in our reply message header. Right, this thing is null. So if we go back one step, this thing will become something with the reply what, which is what we expect. Yeah, and here it should do what it needs to do. So now we continue, and somehow we did not. We are hanging somewhere. We should have reached this second invocation of helper, or invoked this for a second time. We did neither. Are we locking this spoofer here too often? Let's put a breakpoint here. This might of course be a problem as well. Message, so we are here, we are here, we are here. Let's inspect the client. Threads, main thread. Try send, write data, helper, port reply. It says it's waiting on the on this thing, but we only have seen it being invoked once. Request what we have. Just try it again. Okay, so we have here our first helper, which is correct. We arrive here. Let's remove all the breakpoints on the server side. Let's basically remove all the breakpoints except for very few. So we want to... Actually, we could just really step through this now step by step. So we get... This thing never finished this time, so we have apparently broke something on the server side, because this thing should finish the operation, and it never did. Let's put a breakpoint here. Let's see what the server does. Okay, so we are here in our request to do something. We prepared the request, we prepared the replay buffer, replay port, replay buffer, in use is cleared. And then here we should reply. So we have reply pod, which we have set. We have reply message, which we can check. That doesn't look valid. What did we do wrong? Apparently we have cleared some information which we were not supposed to clear. Okay. So we know this part was fine. Let's put a breakpoint here. So we have our reply message, which is shouldn't be hello, it should be what? That's one bug already. No, it did not prepare a reply. Okay, let's put a breakpoint here. I guess we will not be reaching this point after all. Yeah. But now it's stepped over it. Even though there was no reply. Then we are again here. It looks again like some sort of timing error. This thing should so if we reply instantly, it somehow doesn't do what it should. And now it works. Weird. Okay, let's take this as a let's take the win. We can debug this later why this behaved in this strange way. So let me go to our socket again. So server connect. We have the first message, then want to go the second time, and then doing the second invocation of this thing, we should then reply with our reply message. Let's put a here. So we should have replayed something. Then the replay pod will be cleared and the message will be cleared as well. Okay, then type 01, which one was it? Request. And this was 0, this was 0, so we were also not replaying, so this is also set to 0. This is good, and on the servers, on the client side, we should have been here already then for a right, let's put this breakpoint in charge. So let's rerun it with this. Don't know, let's first keep this breakpoint here. We'll see whether we will be getting a proper response. This we don't care. Okay, we get first iteration is empty and the second one is also empty. This is not quite right. The second time we come here, we should have gotten something. So there was something not right here with our reply message. Let's again run it. So that's just pod creation. Then we connect the client. We get a pod. Then we get a request. This is already not null. Right, then we get the first iteration, and then we go in the second time here, and then this should contain our reply, but it does not. It does not. So something in our logic is not quite right. Let's the breakpoint here again. Zack, and this we don't care for now. Connect client, zack, zack. That is correct. Then we have another request. Now we again have the issue that we do not trigger this port reply. So it seems like our trick with the queued blocking connection to get the signals to force here asynchronization like this is not quite working if we remove too many breakpoints. So if we have some breakpoints around, then this seems to work. But if we don't, then it fails. So we will need to fix this later. But for now, let's try if we can at least see one successful communication. Oops, I pressed client twice. That might cause unexpected behavior. Let's try it again. Zack. Okay, so we have this. Then we create a client. Wait, reply, nothing. Then this. This is again null, and this time it didn't work. I mean, we could of course add here an artificial wait to ensure that there is something in the reply buffer that kind of breaks the semantics of how this should work Qt wise, but just for testing, I mean, on the other hand, we should not be relying on the user always selecting the blocking connection type anyway. So what we can do here is that we wait on helper. So we had the mutex log somewhere. So for mutex log, but here we are again not where we should be. With regard to we are not we don't have access to the interesting part. So let's add the wait here. So actually we already have the log, so we can just relog. We could relog it. Wait, we need to unlock it. We want to relog unlock, and if is the helper send buffer size is equals is greater 0, then we break. We don't need unlock because unlock will be automatic once we leave the scope of where lock was defined. And as we wait sleep 10 milliseconds. Okay, so I activate this breakpoint. Server, we remove that breakpoint. We run it. We go into our request, and the thing is hanging. Do we break something else? Output. There is no. Here we are more or less here the whole time, not getting anything from our send buffer. Okay, but since we have this here, we could or should remove the blocking unblocked. Sorry, we were looking for yeah. So here, let's remove this temporarily. of course possible that we broke something else, but that's rather unlikely. Server client. Yeah. Nope. We have, while changing things, we have broken something else. We are not getting a ready read event anymore at all. Port server Qt. So apparently we are not entering this function here, or the write is broken. That's also possible. Request. Yeah, the thing is hanging. That is not great. Request. We put a breakpoint here. We see that we emit something, and then we have here the relog and the waiting in the endless loop. And unfortunately, we are not getting the ready read event anywhere. What did we break? We broke something. I think the only change we did was to create this helper object somewhere else and then work with it. And the difference is that now we are creating it in the helper thread instead of creating it in the thread which is asking for it. So I think this will be the problem, since the thread affinity affects the behavior of this signals and slots, although we didn't get a warning, which is also concerning. There should have been normally a warning when such a thing happens. Right, but then it here will not be happy. Okay. We will need another helper function. We have deleted here one helper function. This one. Let's call it no, we don't need to call this anything. This happens on at the right point in time, so it probably socket this happens in the right thread. Just the helper is not in the right thread, so we will move the helper where it should belong to. Helper, move to thread. I see another problem. There is another problem that complicates the whole thing. That is being that we try to emit the signal before the connection is established. This is why this is failing. Maybe this might be the only reason why this is failing. So for now, so moving this is definitely the right thing to do, because we want the helper to live in the same thread as this thing. But the problem will really be that we kind of need to reissue this ready read if there is something to be read. once the connection has been established. Okay, for now let's comment this test code out. I think we found the error. Server. Right, this gets here. Hmm. Where we create the socket. And then make open, and the problem here still will be that the other end, so to say, of the whole connection will still not be connected. This will require a hacky solution, but okay. Qtimer, single shot, 10 Millisekunden. That socket might not exist at this point in time anymore. That is also not quite ideal. Helper will. We capture helper as a copy, not as a reference. Then if this will need to be a function which we can call from anywhere helper and although maybe we should just add a convenience function. Is already read is receiving, but just for the receive buffer. Alright, and of course we should lock the thingy. This was also a small mistake. We need to lock the buffer, otherwise we not be safe. And so here just if helper is receiving, then emit helper ready read. Okay. Yes. So this gives a very small delay, 10 milliseconds, which is more than enough for the operation here to complete, because where is it? Here we get the socket and then we do our thing, and we want this to be done. If in principle, no matter how long this would take, the timer will not shoot at 10 milliseconds, but at the earliest opportunity after 10 milliseconds, when the event loop of the current thread is empty. So as long as this thread would be here doing things and waiting, the timer wouldn't shoot anyway. So this should solve the issue. I guess I broke something. Looks like a comma is missing somewhere in a header or a closing bracket or something. Log. Oh yes. It doesn't like. So here when we are logging the mutex, this is a const function, so we need to define the mutex as mutable, and should be happy. So connect, send. Okay, so we have here our request, we have here our do something. This didn't seem to have improved at all. I mean, that makes sense, because this thing here was not longer locking it. It was just kind of ignored, and then in the next go through it was it was executed. But we have not reached this. Current thread is not the object thread. That is also not great. Doesn't like the move to thread being done from a different thread. It only wants this move to be executed from the thread the thing currently belongs to. So let's ignore this and try something else. Now we just want to see that we get the event at some point. Yeah, so this worked. The question, but this worked because of our timer hack. So yeah, tick. So here we have a reply which doesn't do anything. Then we bug out there. Then here we have our hack that causes the thing to shoot, which then works. Just that then when we prepare something to be replied, we already here have bugged out. We could make it demand to receive something. So basically just make this run in a loop on the last invocation until we get some reply. Wouldn't be pretty, but would be a quick workaround for now. And we are already running out of time, so we should go with that. So as you see, there are still a few things that will need improving on the whole thing, but where's the hyperfunction? Here. Let's call it yeah, 32 timeout, and by default it's 0, and else it will not be 0. So here let's give a timeout of 3 seconds. The other one has 0, so the other one will not wait for anything. Then here we need our timeout. And yeah, basically if this happens, here we are checking if we are we should also note if we have received something. So reduce, let's found receive total. Right, and if we received something, then receive total plus equals header length. Right, okay, so if we have 0 and if receive total is 0 and timeout is more than 0, then we want to repeat the whole thingy. Continue. And then we need to somehow make our timeout work. Ideally you would create a queue timer and count the elapsed time. Yeah, why not? Let's make this elegant. Timer. If timeout timer start, and if timeout is greater 0, then we do something. If timer elapsed is greater timeout, then we break, else we continue. Okay. Well, not great, but should be a workable temporary fix. For later we will need to find a more elegant way, because we don't want such heavy-handed approaches in production code. So we have this thing. Now we send some data and it didn't work, or why? Did we try to continue? We went into continue once, into continue twice. Now replying. Oh, okay. Response buffer. Something is still not quite right. First of all, we will change the timeout to something longer, because 3 seconds is really too short. So especially if we are stepping through breakpoints, just go 30 seconds. And we should add at least some delay. Red msleep. Say we wait 10 milliseconds, 110. Let's go with. Actually, we could just go with 1 second for now. Don't care for this. We will make a log message. And we say how long we have been waiting. Okay, and let's remove all the breakpoints from the client side. We will be able to observe the client in the event log as it is waiting. So we have here, we have this, we have this, we have this. And this thing is, now it's no longer waiting unless it is it retried. It didn't seem to have received any data. And now it's stuck. Let's see if it's stuck in the wait replay port. Okay, since we're running out of time, I think this is a good point to stop. I will debug this, and in the next lecture we will continue with this being fixed, and I will explain the fix, what was going on here, that it didn't manage to successfully send a reply. Yeah, any questions so far?
I would have another question regarding the final project
Yes.
that came to my mind. Shall we do like a little documentation or like write something where you can find each function? So for example, okay, you have to do a right click on a list entry, and then you can choose the color thickness or something like that.
I think a README, right? A little
Yeah.
text file.
You can do that, but that is not mandatory. So it just see it as a optional option. So if you do it, it will
Okay.
give you some extra points.
Okay, thank you.
Any more questions?
Yeah, I have one regarding next semester.
Yes.
Will you be doing the part 1 course again? Because
Yes.
I haven't
Correct.
actually done that. Okay. So will that be similar to this course right now, or is there going to be changes?
Well, there will be no Qt. We will be looking on C++ only and the
Uh-huh.
lower levels aspects of that.
Okay.
Yeah, but from the mode it will be similar. It will be a lecture with some homework and the final project.
Okay. Okay. All right. Thank you.
You're welcome. Any other questions?
Not from me.
Okay. Then I guess let's stop the recording.